Look up at the night sky and pick a single star. Hold it in your gaze. You believe you are standing still beneath it. You are not. At this exact second, your body is being carried through the galaxy at roughly 220 kilometers every second, faster than any rocket ever built. The neat little diagram of planets circling a fixed sun is a lie of convenience. The real shape of our home is something stranger and far more beautiful. Dim the lights, let your shoulders drop, soften your jaw, and take one slow breath in. Then let it go. Tonight, we will climb outward through 6 nested frames of motion, from the spin beneath your feet to the sun's long arc around the galaxy, to the silent current of the local group, to the strange dipole written across the cosmic microwave background, and discover why nothing in the universe has ever, even once, been truly still. Before we dive in, if you love exploring the architecture of the cosmos as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. I read every comment. Now, let's begin. Everyone knows how the solar system works, or thinks they do. The poster on the classroom wall, a fat, golden sun at the center, and planets riding around it on neat ellipses, each in its own lane. The lines are flat. The sun does not move. The whole machine looks like a pocket watch ticking quietly in some empty corner of the void. That picture is almost entirely wrong. Not the names of the planets, not the order, not even the rough shapes of the orbits, which are indeed ellipses, very nearly circular, very nearly flat with respect to one another. What is wrong is the frame. What is wrong is the assumption that anything in that diagram is sitting still. The sun on your classroom wall is anchored to the page. The real sun is not anchored to anything. It is sprinting through interstellar space at a speed that would melt your intuition if you tried to feel it. And as it sprints, it drags every planet, every moon, every grain of dust, every passing comet, every spacecraft we have ever launched with it. The orbits in the textbook are real, but they are also a kind of optical trick, a snapshot taken from a viewpoint that does not exist. If you stepped outside the system, if you parked yourself in the cold dark a few light hours away and watched the sun pass by, you would not see flat ellipses. You would see something that looks more like a long, slow corkscrew threading itself through the galaxy. You would see helices. You would see drift. You would see a tiny, glowing comet of a star pulling a ribbon of planets behind it through the night. That is what we are going to look at, layer by layer, frame by frame. Not just the motion of the planets around the sun, but the motion of the sun through the local neighborhood of stars, and the motion of that neighborhood around the galactic core, and the motion of the galaxy itself within the local group, and the motion of the local group across an even larger flow of galaxies, and finally, the motion of all of it against the oldest light in existence, the cosmic microwave background, which is the closest thing the universe has to a still photograph of itself. Each frame will change what you think you mean by the solar system. Each frame will redraw the picture in your head. By the end, the pocket watch in the textbook will be unrecognizable, and you will understand why astronomers, when they speak carefully, never really say that the Earth orbits the Sun. They say the Earth and the Sun orbit each other around a shared point. And that shared point is itself orbiting something larger, which is itself orbiting something larger, and so on, outward in a cascade of motions that does not resolve into stillness at any scale we have yet been able to measure. To get there, we need to begin with the simple version. Not because it is right, but because it is the version your body trusts. Your body believes the ground is still. Your body believes the sun rises and sets. Your body believes the stars are tiny lights pinned to a dome. Every cell of your perception is built around a stationary Earth, and to dislodge that belief, even for a few hours, requires care. So we are going to start where the textbook starts, on the surface of a small rocky planet with a glowing companion in the sky. And then we are going to begin pulling at the threads, gently, one at a time, until the entire picture comes apart and reassembles itself into something almost unrecognizable. The first thread is the Earth itself. You are standing on it, or sitting, or lying down. Whatever your posture, the floor beneath you feels solid and reliable, and most importantly, motionless. It is not. The Earth turns on its axis once roughly every 24 hours, and at the equator that rotation carries you through space at about 1,670 kilometers per hour. Closer to the poles, the speed is less, because the circle you trace as the planet spins is smaller. Wherever you are on Earth, unless you are exactly at the North or South Pole, you are spinning. You are being carried sideways through the air around you faster than a passenger jet flies. You do not feel it because everything around you is spinning at the same speed. The air, the trees, the buildings, the oceans, the very ground. Motion that is shared by every reference point in your immediate environment becomes, for all practical purposes, invisible. This is the first and most important lesson of cosmic motion, and it will return again and again as we climb outward through scales. Motion becomes visible only when something else is not moving with you. Take that away. Give everything around you the same velocity, and the motion vanishes from your senses, even though every measurement instrument in the world will confirm it is there. So, the Earth spins. That is motion number one. But the spinning Earth is also moving in another way, a much grander way, because it is bound to the Sun by gravity. The Earth orbits the Sun once roughly every 365 days, and to do so, it is traveling along its orbital path at about 30 kilometers per second. 30 kilometers in a single second. By the time you have read this sentence, the Earth has moved more than 100 kilometers along its orbit, and you have moved with it. By the time we reach the end tonight, the Earth will have traveled more than 200,000 kilometers, more than half the distance to the Moon, through the empty space around the Sun. Again, you do not feel any of this. The Earth's orbital motion is shared by everything on the planet. The Sun, from your point of view, simply seems to drift slowly across the seasons, higher in summer, lower in winter, a long, lazy oscillation that is in fact a side effect of the planet's tilt and orbit combined. The orbit itself is invisible to your senses. The only way to know it is happening is to measure something that is not coming along for the ride. The other planets, the distant stars, the way certain stellar positions shift infinitesimally over the course of a year, as we view them first from one side of our orbit and then 6 months later from the other side. This shift, called parallax, was the first hard evidence that the Earth genuinely moves. It took until the 1830s for a measurement precise enough to detect it. Friedrich Bessel, in 1838, finally measured the parallax of a star called 61 Cygni, and in doing so, gave humanity the first confirmed proof that we live on a moving world. Until then, every claim that the Earth orbited the Sun rested on inference and theory. Bessel's measurement made it physical. Pause for a moment on that. For most of human history, no one alive could prove the Earth was moving. The Greeks debated it. Aristarchus of Samos, in the 3rd century BCE, argued for a heliocentric model in which the Earth orbited the Sun. He was not believed. Copernicus revived the idea in the 1540s, and he was largely ignored for decades. Galileo, in the early 1600s, pointed his telescope at Jupiter, saw moons orbiting that planet, and realized he was watching a small heliocentric system in miniature. He was placed under house arrest. Newton, later in the same century, gave the motion a mathematical foundation so complete that no other model could compete. But still, no one had directly measured the Earth's motion. The proof came almost 2,000 years after Aristarchus first proposed it. Bessel watched a star, the star wobbled, and the Earth's motion became, at last, a fact rather than a hypothesis. We tend to forget how recent that is. The phone in your pocket is a more sophisticated piece of technology than anything Bessel had access to. The fact that the Earth orbits the Sun was, until astonishingly recently in human history, a controversial scientific claim. So that is motion number 2. The Earth orbits the Sun. But here is where the simple picture starts to get interesting, because the Sun is not at the center of the Earth's orbit. Not exactly. The Sun and the Earth both orbit a shared center of mass, what astronomers call the barycenter, and that point is offset slightly from the geometric middle of the Sun, because the Earth is not massless. It is small compared to the Sun, true. The Sun outweighs the Earth by a factor of about 333,000. But 333,000 is not infinity. And so, the Sun gently, almost imperceptibly, wobbles in response to the Earth's pull. When you add Jupiter to the picture, the wobble becomes more dramatic. Jupiter is more than 300 times the mass of the Earth. It is so massive that the barycenter of the Sun-Jupiter system actually lies just outside the surface of the Sun. As Jupiter orbits, the Sun is yanked back and forth around that point, in a small but measurable circle, every 12 years. Add Saturn, Uranus, Neptune, the inner planets, the asteroids, the dwarf planets, the comets, and the Sun's motion in the local frame becomes a complicated tangle of overlapping wobbles, a slow dance with each gravitational partner pulling in its own direction. This is already a richer picture than the textbook. Already, the Sun is not a fixed center, but a kind of weighted ball at the heart of a many-body dance, swinging in small loops around a constantly shifting barycenter. And we have not even left the solar system yet. We are still, at this point in our zoom, looking at the local neighborhood. We are still pretending the Sun, on average, sits in one place, and that the planets dance around it. But the Sun does not, on average, sit in one place. The Sun is moving. It is moving as a whole. It is sprinting through the galaxy, and as it sprints, it is dragging the planets, the asteroids, the comets, the dust, the heliosphere, and us along with it. The orbits we trace around the Sun are real, but they are superimposed on a larger motion that no schoolroom diagram has ever shown you cleanly. To see that motion, we have to step outside the solar system entirely and look back at it from the perspective of the stars. That is where we are going next. Out into the local neighborhood, into the patch of the galaxy that contains our nearest stellar neighbors, and into the discovery, made more than 2 centuries ago, that the Sun itself is on the move. To step outside the solar system, even just in our imagination, we need to first establish how big a step that is. The Earth is about 150 million kilometers from the Sun. Light, which moves faster than anything else in the universe, takes about 8 minutes to make that crossing. The next nearest star, a small red dwarf called Proxima Centauri, is more than 4 light years away. Light takes more than 4 years to cover that distance. To travel from the Sun to Proxima at the speed of the fastest spacecraft humans have ever built, the Parker Solar Probe, which during its closest passes through the Sun's outer atmosphere reaches speeds of nearly 700,000 kilometers per hour. would still take more than 6,000 years. 6,000 years is the fastest thing we have ever made, just to reach the nearest star. This is the gulf we are trying to picture. The sun is alone out here. The planets cluster around it like moths around a single lamp. And beyond them, for unimaginable distances, there is almost nothing. A few comets in the Oort cloud, drifting at the edge of the sun's gravitational influence. Some dust, some plasma. And then, finally, after a journey that dwarfs the entire scale of the planetary system, you arrive at the next nearest star. Now imagine you are out there. Park yourself in interstellar space, halfway between the Sun and Proxima. Look back. The Sun, from this distance, is not a brilliant disk. It is not even particularly bright. It is just one star among millions, slightly yellower than its neighbors, indistinguishable to the naked eye from any of the thousands of other points of light around it. The planets are invisible without a powerful telescope. The whole solar system from this vantage is reduced to a single dot. And then you wait. Years pass, decades, centuries. And as they pass, you notice something you would never have seen from the ground. The dot is moving. Not in a circle, not in any kind of orbit. It is moving in a straight line. Well, very nearly straight. On cosmic scales, very few things move in true straight lines, drifting steadily across the background of more distant stars. The sun, you realize, is going somewhere. It is heading toward a particular point in the sky, and it is moving fast. This is not a thought experiment. This is a real measurement, and the first person to make it was William Herschel in 1783. Herschel, the same astronomer who discovered Uranus, was poring over the recorded positions of stars and noticed a pattern. Stars in one part of the sky seemed, on average, to be drifting apart from each other. Stars in the opposite part of the sky seemed, on average, to be drifting together. He realized, brilliantly, that this was exactly what you would see if the sun itself was moving. That the stars were not all drifting independently, but that we were moving through them, and the geometry of our motion was being written across the heavens. Drive a car through a forest at night, and the trees ahead of you seem to spread apart as you approach, while the trees behind you seem to converge in your rearview mirror. The same pattern, on a vastly slower scale, is visible in the stars. Herschel calculated from this pattern that the sun was moving toward a point in the constellation Hercules. He called this point the solar apex. It is the direction the sun is traveling, the direction of our forward motion through the local stellar neighborhood. And the point we are moving away from, on the opposite side of the sky, is called the solar antepex, in the constellation Columba, the dove. Take a moment with that. Right now, as you listen, your entire solar system, every planet, every moon, every spacecraft, every grain of dust caught in the sun's gravity is barreling toward a specific point in the night sky. If you live in the northern hemisphere, you can find it. Look high overhead in the late spring and early summer, near the constellations Hercules and Lyra. Somewhere in that direction, hidden behind the brighter stars, is the point in space the sun is racing toward. We will never reach it, of course. By the time we are anywhere near it, our motion will have carried us off in some other direction, because our path through the galaxy is not a straight line. It curves. But for now, on the scale of human lifetimes, we are heading there. How fast? The sun, relative to the average motion of the stars in our immediate neighborhood, is moving at about 13 to 20 kilometers per second, depending on the method used to define the local average. That neighborhood averaged frame of reference has a specific name in astronomy. It is called the local standard of rest, or the LSR. Imagine averaging the motions of all the stars within a few hundred light years of the Sun. Some are moving faster, some are moving slower, some are moving in different directions. Take all of those motions and average them, and you get a kind of mean velocity, a baseline drift that everyone in this neighborhood is participating in. The Sun is moving relative to that baseline at about 20 kilometers per second toward Hercules. 20 kilometers per second in human terms is staggeringly fast. It is faster than any human-made object except for spacecraft launched on deliberate gravity-assist trajectories. It is roughly 72,000 kilometers per hour. At that speed, you would cross the United States coast to coast in about 3 minutes. You would circle the Earth in about 10 minutes. And the Sun is doing it constantly, every second, every minute, every hour, hauling its retinue of planets along behind it through interstellar space. But here is where the picture starts to get interesting again. Because that 20 kilometers per second is the Sun's motion relative to the local average. It is not the Sun's total motion. The local average itself is moving. The whole stellar neighborhood, the LSR, is itself in motion, and it is moving much, much faster than the Sun's local drift. To see that, we have to zoom out one more step and look at the Milky Way galaxy as a whole. But before we zoom out, stay here for a moment longer. Stay in the neighborhood, because the local picture has more to show you. Within a few tens of light years of the Sun, there are several hundred stars. Most are smaller and dimmer than our own. Red dwarfs mostly, the most common kind of star in the universe. There are a few stars roughly the size of the Sun. There are a handful of giants, and among them, there is a particular feature that astronomers have come to call the local bubble. This is a region of space, roughly 300 light-years across, in which the density of interstellar gas is much lower than the surrounding galaxy. We live inside it. The local bubble is, very plausibly, the result of one or more supernova explosions a few million years ago. Stars that died in titanic blasts and blew out a cavity in the surrounding interstellar medium, leaving behind a bubble of relatively empty space. Our solar system happens to be drifting through this bubble at the moment. We did not always live in it. We will not always live in it. We are passing through, like a fish passing through a region of slightly clearer water. And inside the local bubble, embedded within it, is a smaller cloud of gas called the local interstellar cloud, sometimes nicknamed the local fluff. The Sun is currently flying through this cloud. The fluff is roughly 30 light-years across, with a density still lower than most parts of the galaxy, but higher than the rest of the bubble. We entered it sometime in the last 100,000 years. We will exit it, possibly, sometime in the next 50,000. The Sun's heliosphere, the bubble of solar wind that defines the boundary of the solar system, is being shaped right now by the pressure of this cloud as we plow through it. Take a breath here. This is the first paradigm shift the topic asks of you. The solar system is not a fixed object. The boundary of the solar system, the edge of the Sun's influence, is being squeezed and stretched by the local interstellar weather, and that weather changes as we move. A few 100,000 years ago, the heliosphere may have been larger. 1,000,000 years from now, when we have moved into a different region, it may be larger again or smaller. The shape of our home is not constant. It breathes slowly in response to where in the galaxy we happen to be. And here is something else. The motion of the Sun toward Hercules, at 20 kilometers per second, is not the speed of the Sun through the gas of the local cloud. The cloud itself is moving. Relative to the cloud, the Sun is moving at a slightly different speed, in a slightly different direction. Multiple frames of reference are layered on top of each other, each one telling a different story. The sun's motion through the LSR is one story. The sun's motion through the local cloud is another. The sun's motion through the local bubble is yet another. None of them is the right answer. They are all the right answers depending on what question you are asking. This is the second lesson of cosmic motion, and it is more profound than the first. There is no single velocity for the sun. The sun's speed depends entirely on what you measure it against. Pick a different reference frame, and you get a different number. There is no privileged background, no cosmic ground floor, no absolute, this is how fast the sun is really moving. Every measurement is relative to something else, and that something else is also moving. This is going to come up again and again. Hold on to it. Now, the textbook answer is that the Earth orbits the sun. The textbook answer is that the planets move in flat ellipses. The textbook answer is correct in the frame of reference of the sun. But the moment you step outside that frame, the moment you anchor yourself to anything else, the local stars, the galactic core, the cosmic microwave background, the picture changes shape. The orbits stop being closed loops and start being helices. The sun stops being a fixed center and starts being a moving target. The planets stop tracing tidy ellipses and start tracing long, curving spirals through space, never returning to exactly the same place twice. This is a profound consequence of the relativity of motion, and it deserves to be sat with for a moment. Imagine you are watching a child on a playground swing. From your point of view, standing still on the ground, the child swings forward and back in a clean arc. Now imagine the playground itself is on the back of a truck, and the truck is driving down the highway at a steady speed. From your point of view, standing on the side of the road, the child is no longer swinging in a clean arc. The arc is being stretched out into a long, looping curve. Each forward swing is carrying the child a little further down the road. Each backswing is bringing the child back toward where the swing was attached, but the truck has moved. The child traces, instead of a closed arc, a kind of wave through space, never returning to the same point twice. That is what the Earth is doing right now. The Earth orbits the sun, yes, but the sun is on the truck and the truck is moving. The Earth's orbit, viewed from outside the solar system, is not a flat ellipse. It is a helix. It is a corkscrew. It is a long, slow spiral that winds around the sun's path through the galaxy, completing one loop per year, while the sun itself drifts toward Hercules at 20 kilometers per second. Your body, right now, is on that helix. You are not orbiting the sun in a closed loop. You are riding a spiral through interstellar space, and the spiral never closes. You will never return, in any absolute sense, to where you were a year ago. The position you occupied last summer, the actual spatial coordinates in the frame of the local stellar neighborhood, is now hundreds of millions of kilometers away. Gone, behind us, lost in the wake of the sun's passage. Your body has never been in the same place twice, and it never will be. Stay with this for a moment. The implications are quietly enormous. Every birthday you have ever celebrated, every anniversary, this is where I was a year ago. All of those are illusions of frame. In the sun's frame, yes, you are roughly back where you started. In the galaxy's frame, no. You have moved an unimaginable distance. The space your body occupied at this same moment last year is not waiting for you to return to it. It is empty now. Space has flowed past, and we have moved on. This is why the textbook diagram is, in a deep sense, a comforting fiction. It freezes the sun. It cancels out the larger motions. It gives you a frame in which orbits are closed and time is cyclical, and the same configurations repeat year after year. And for many purposes, that is all you need. For navigating spacecraft within the solar system, it works perfectly. For predicting eclipses and tides and seasons, it works perfectly. But it is not the truth. It is a useful local approximation, and the moment you step back, even slightly, the approximation breaks down. Now we are going to step back further. We are going to leave the local neighborhood entirely and look at the Sun's place in the galaxy as a whole. Because the 20 kilometers per second toward Hercules is, as I said, only the Sun's motion within its immediate stellar surroundings. The surroundings themselves are moving around the heart of the Milky Way, and the speed of that larger motion is more than 10 times greater than the local drift. 220 kilometers per second, the number you may have wondered about at the start of this journey. That is, very roughly, the speed at which the Sun and its neighborhood are orbiting the center of the Milky Way galaxy. 220 kilometers in a single second. Let that sink in. The Earth orbits the Sun at 30 kilometers per second. The Sun, as part of the local stellar neighborhood, orbits the galactic center at more than 7 times that speed. Right now, as you listen to this sentence, you are being carried through the galaxy at over 790,000 kilometers per hour. The picture has gotten larger, much larger. To make sense of this number, we need to understand what kind of object the Milky Way is and where in it the Sun lives. So let us set up that picture carefully. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across, containing somewhere between 100 and 400 billion stars, depending on how you count and what you include. Most of those stars are arranged in a flat disk, with a thicker bulge of older stars in the center and a halo of even older stars and dark matter surrounding the whole thing. The disk has spiral arms, sweeping curves of higher star density where new stars are forming, where bright young blue stars cluster, where dust lanes shadow the light from behind. From above, if you could float far enough out and look down, the Milky Way would look like a pinwheel, slowly turning. From the side, it would look like a thin disk with a glowing bulge in the middle, like 2 fried eggs placed back to back. The Sun is not at the center of this galaxy. The Sun is in the disk, but well out from the core, about 26,000 light-years from the galactic center. We live in a relatively quiet, relatively unremarkable part of one of the spiral arms, actually, more precisely, in a smaller feature called the Orion Spur, or the Orion Arm, which is a kind of side branch between 2 of the major spiral arms, the Sagittarius Arm closer to the galactic core and the Perseus Arm farther out. We are in a galactic suburb, not the bright bustle of the inner city, where stars are packed densely and supernovae go off frequently. Not the lonely outskirts, where stars are sparse and the light fades. A nice middle distance, a nice middle arm, a nice middle place to grow a planet that does not get cooked by radiation or starved by isolation. And from this nice middle place, we are orbiting the center of the galaxy, once, slowly, endlessly, at 220 kilometers per second. How long does one orbit take? At that speed, at that radius, a complete trip around the galaxy takes roughly 220 to 250 million years. Astronomers call this a galactic year. The exact figure is contested. Different measurements give slightly different values, and the orbit is not a perfect circle. But the order of magnitude is solid. 250 million years to circle the galaxy once. The Earth, since its formation roughly 4.5 billion years ago, has completed somewhere between 18 and 20 galactic years. That is all. In the entire history of our planet, we have orbited the galactic center fewer than 20 times. 20 galactic years, less than the lifespan of a long-lived dog in the units of the galaxy itself. The dinosaurs went extinct about 250 galactic days ago, if you scale a galactic year to a human year. The first hominids stood upright maybe 2 galactic hours ago. Recorded human history fits comfortably in a galactic minute. We are infants in galactic time. The sun has barely begun to learn the shape of its own orbit. And yet, in those few orbits, the sun has done something remarkable. It has carried us through wildly different parts of the galaxy. 200 million years ago, when the first dinosaurs were beginning to walk, the sun was on the opposite side of the Milky Way, in a region of space we cannot now even directly observe, because the galactic core sits between us and our former location. 400 million years ago, when the first forests were rising on Earth, we were somewhere else again, in yet another stretch of the spiral arms, surrounded by stars that have since drifted apart and dispersed. The neighborhood we live in now is not the neighborhood we lived in when life began. It is not the neighborhood we will live in when humans are gone. The sun's orbit around the galaxy is gentle by galactic standards. It is roughly circular. It does not plunge through the dense inner regions where supernovae are common, where radiation levels are high, where gravitational disruptions might strip planets from their stars. It stays out in the suburbs, looping calmly through the disk, dipping a little above and below the central plane in a slow vertical oscillation that takes about 65 million years to complete. Some astronomers have wondered whether that vertical bobbing, up through the disk, down through the disk, up again, might correlate with mass extinction events on Earth. The galaxy's central plane is thicker with stars and dust than the regions above and below it. When the sun passes through the densest part of the disk, perhaps it encounters more cosmic perturbations, gravitational nudges that send comets spilling out of the Oort cloud and toward the inner solar system. The evidence for this is contested. Some researchers think the correlation is real. Others think it is a coincidence of small numbers or an artifact of how we measure extinction events in the geological record. We do not know. But the possibility hangs there, quietly, in the back of every conversation about the sun's galactic orbit. Our species' existence may depend, in some small way, on where in the disk we happen to be at this moment in the orbit. This is the next layer of motion to absorb. The sun is not just sprinting toward Hercules at 20 kilometers per second. It is also being carried, along with its entire local neighborhood, around the galaxy at 220 kilometers per second. The two motions are superimposed. The Hercules motion is a small drift on top of the much larger galactic orbit. To picture it, imagine a runner moving across the deck of a moving ship. The runner has their own velocity, 20 kilometers per second toward the bow. But the ship is moving at 220 kilometers per second in some other direction. The runner's actual velocity through the water is the sum of those two, mostly the ship's motion with a small adjustment for the runner's stride. That sum, the sun's velocity through the galactic frame, is what astronomers refer to when they speak of the sun's galactocentric velocity. It is the speed at which we are moving around the heart of the Milky Way, including all the local complications. The number is around 230 kilometers per second, depending on which study you read. The sun is racing around the galaxy at that speed, pulling all of us with it, and tracing out a path that is not, in any closed sense, a repeating orbit. The galactic year is real, but the sun does not return to exactly the same place after each one. The galaxy itself is in motion. The orbit drifts. The sun spirals slowly outward, perhaps, or inward, perhaps. Other stars perturb us. The galactic bar, that thick, straight-edged feature in the central regions of the Milky Way, pulls on us slightly, in patterns that change over hundreds of millions of years. Nothing is fixed. Nothing closes. Nothing repeats exactly. Now picture, in your mind, what the Earth's orbit looks like in the galactic frame. The sun is moving around the galaxy at over 200 kilometers per second. The Earth is orbiting the sun locally at 30 kilometers per second. The Earth completes one full orbit around the sun in a year. In that same year, the sun moves through the galaxy by roughly 7 billion kilometers, about 45 times the distance from the Earth to the sun. So the Earth, viewed from the galactic frame, does not trace a flat ellipse. It traces a long, gentle helix, a corkscrew that loops once per year around the sun's much faster path. The diameter of the helix is about 300 million kilometers, the diameter of Earth's orbit. The pitch of the helix, how far it advances each year along the sun's direction of motion, is 45 times that diameter. So it is not a tight spring. It is a stretched coil, a long sweeping curl. But it is still a helix. It still never repeats. The Earth has never been in the same place twice in the galactic frame, and it never will be. This is where many internet diagrams have started showing the solar system as a kind of vortex, with the planets trailing behind a moving sun like the tails of comets. Those diagrams are partially right and partially wrong. The geometry of helical motion is real. The Earth and the other planets do trace helices in the galactic frame. But the diagrams often exaggerate. They show the solar system tilted at some dramatic angle, with the planets dragging behind. The reality is gentler. The plane of the solar system, the plane in which the planets orbit, is tilted relative to the sun's direction of motion through the galaxy by roughly 60 degrees. Not perpendicular, not parallel. Somewhere in between. The planets are not really dragging behind. They are looping forward and back along the sun's path, sometimes ahead of the sun, sometimes behind, depending on where they are in their orbit. The shape, viewed from outside, is not a comet tail. It is more like a long, leaning corkscrew, with each planet drawing its own coil at its own scale. Mercury, closest to the sun, traces tight, fast helices, completing each loop in about 88 days. Earth traces slower, wider helices, one loop per year. Neptune, far out at 30 times Earth's distance, traces vast, lazy helices, taking 165 years to complete a single loop. From the galactic frame, the solar system is a nested set of helices, each at its own pitch, each at its own scale, all of them advancing together along the sun's path through the galaxy. None of them ever closes. None of them ever returns. The textbook ellipses are local snapshots. The galactic reality is a slow, endless spiral. Stay with that image for a moment. Stay inside it. Picture yourself riding the Earth's helix, looping once per year around the moving sun, looping endlessly forward through the galaxy. Picture the planets ahead of you and behind you, each drawing its own coil. Picture the sun, dragging the whole system through the dark, never stopping, never slowing, never returning to where it has been. This is what your home looks like when you stop pretending the sun is fixed. This is what motion looks like when you let yourself see it. Now, let us go further. The sun's 220 kilometer per second orbit around the galactic center is, of course, not the end of the story. The galaxy itself is not standing still. The Milky Way is part of a larger structure, a small group of galaxies bound together by gravity, called the local group. And the local group is in motion. And the local group is part of a still larger structure, and that is in motion too. Every layer outward, every zoom, reveals another speed, another direction, another vast frame of reference in which our previous answer was just a local approximation. To see the Sun's place in the Milky Way more clearly, consider the work done in the last few decades using radio observations of distant masses. Natural laser-like beams of microwave radiation produced in dense regions of star formation. Massa sources can be located very precisely, and by triangulating their positions over time, astronomers can map the rotation of the galaxy with extraordinary accuracy. In 2014, a team led by Mark Reed at the Harvard-Smithsonian Center for Astrophysics published one of the most refined measurements of the Milky Way's rotation curve to date, using an array of radio telescopes called the Very Long Baseline Array. Their results suggested that the Sun's orbital speed around the galactic center is closer to 240 kilometers per second than to the older textbook value of 220. Other groups, including those analyzing data from the European Space Agency's Gaia mission, which since 2013 have been measuring the precise positions and motions of more than 1 billion stars, have refined the picture further. The current best estimates put the Sun's orbital velocity around the galactic center somewhere between 220 and 240 kilometers per second, with the disagreement reflecting genuine uncertainty in how we measure the gravitational structure of the galaxy. 220, 240. The numbers are similar enough that it does not matter for the picture. The Sun is racing around the galaxy at roughly 250,000 kilometers per second, and the disagreement among researchers is on the order of 10%. That is good science. That is not a sign of confusion. That is a sign that the measurements are now precise enough to argue about. A century ago, no one knew the Sun was in a galaxy at all in the modern sense. The very fact that the Milky Way was one galaxy among many was not established until Edwin Hubble's observations of Andromeda in the 1920s. Before then, most astronomers believed the universe was the Milky Way and nothing else. The spiral nebulae they could see in their telescopes were thought to be small clouds of gas within our own galaxy, not separate galaxies in their own right. The shift was wrenching. The universe, in a single decade, expanded by orders of magnitude. We went from being the only galaxy to being one of an uncountable number, drifting in a vastness no one had previously imagined. So the Sun orbits the center of the Milky Way at roughly 220 to 240 kilometers per second. It also drifts locally toward Hercules at about 20 kilometers per second, relative to the average of nearby stars. Both of these are real motions. Both are happening at every moment of your life, and both are tiny compared to what is coming next. To climb the next step of the ladder, we have to leave the Milky Way itself. We have to think of our galaxy not as a fixed background, but as one object among many, all of them in motion, all of them gravitationally bound to one another, all of them participating in a larger dance. The local group is the small cluster of galaxies of which the Milky Way is a member. There are roughly 80 known galaxies in the local group, though most of them are tiny dwarf galaxies, faint smudges of stars too small to see without sensitive instruments. Two galaxies dominate the local group, our own Milky Way and the Andromeda Galaxy, which is slightly larger, slightly more luminous, and about 2.5 million light-years away. Andromeda is the most distant object visible to the naked human eye. On a dark, clear night, far from city lights, you can see it as a faint smudge in the constellation Andromeda, a soft, slightly elongated patch that looks like a smudge of fog. That smudge is a galaxy. It is 1 trillion stars or more, gathered into a spiral, hanging in the darkness 2.5 million light-years away. Every photon of light from it that reaches your eye left Andromeda before our species existed. The light is older than humanity itself. Surrounding the Milky Way and Andromeda are the smaller galaxies of the local group. The Triangulum Galaxy, the Magellanic Clouds, which are companions of our own Milky Way, and dozens of dwarf galaxies, Sculptor, Fornax, Leo, Draco, and others. Most of them so faint that they were discovered only in the last century. The whole assemblage spans roughly 10 million light-years from end to end, and it is held together by gravity. The galaxies within it orbit one another in long, slow, complicated dances that take billions of years to play out. The most famous dance, and the one most relevant to our story, is the slow approach of the Milky Way and Andromeda. The two galaxies are falling toward each other at about 110 kilometers per second. Current estimates suggest they may collide, in the rough sense that galaxies collide, in roughly 4 to 5 billion years, though recent Gaia data have softened this prediction. Some 2025 analyses now put the probability of a head-on collision at closer to 50% over the next 10 billion years. When they do, the Milky Way as we know it will cease to exist as a separate object. The two galaxies will merge over hundreds of millions of years, their stars passing through one another, mostly without colliding, because the spaces between stars are enormous. But their gravitational structures will rearrange completely. The result, eventually, will be a single elliptical galaxy, sometimes called Milkomeda or Milkdromeda by astronomers with a sense of humor. A fat, smooth, roughly spherical assembly of stars in which the spiral structure of either parent galaxy is no longer visible. The Sun, if it still exists at that point, and it might, since the Sun's lifetime is roughly 10 billion years, and we are only halfway through it, will be flung into some new orbit within the merged galaxy, possibly out into a long elliptical loop that takes us through regions of space we have never seen before. But we are not there yet. We are here. And here, the Milky Way and Andromeda are approaching each other at 110 kilometers per second. Our galaxy is already participating in this approach. Right now, the entire Milky Way, including the Sun, the Earth, your body, every atom of you, is moving toward Andromeda at about 100 kilometers per second. That motion is on top of the Sun's motion around the galactic center, which is on top of the Sun's drift toward Hercules, which is on top of the Earth's orbit around the Sun, which is on top of the Earth's spin on its axis. 5 layers of motion now, 5 superimposed velocities, and we have not yet reached the largest one. To find the next layer, we have to look beyond the local group. We have to ask what the local group itself is doing. Is it drifting? Is it stationary? Is there some larger structure pulling on it? The answer, as you might now suspect, is that the local group is moving. It is moving rather quickly, in fact, and the direction it is moving in turns out to be one of the most intriguing puzzles in modern cosmology. Pull back further. Beyond the local group, the universe begins to reveal larger structures. Galaxies are not distributed uniformly. They cluster. They form sheets, walls, filaments, and voids. Hundreds, thousands, sometimes tens of thousands of galaxies gather together in vast gravitational concentrations called clusters and superclusters. The local group is a small assemblage on the outskirts of one of these larger structures, the Virgo supercluster, which is centered on a much larger gathering of galaxies in the constellation Virgo, about 65 million light-years away. The Virgo cluster contains over 1,000 galaxies. Its gravity dominates a vast region of space, and the local group is part of it, falling slowly toward Virgo, taking part in its great gravitational symphony. But Virgo is not the end either. In the 1970s and 80s, astronomers studying the motions of nearby galaxies began to notice something strange. Galaxies in our part of the universe were not just moving toward Virgo. They were moving towards something beyond Virgo. Some larger hidden mass was tugging on the entire region of space we live in, including the Virgo supercluster, including the local group, including the Milky Way. This unseen attractor lay in the direction of the constellations Centaurus and Norma, in a region of the sky partially obscured by the dense band of the Milky Way's own disk, the so-called zone of avoidance, where dust and stars from our own galaxy block our view of more distant objects. Whatever was pulling on us was hidden behind our own home. In 1987 and 88, a group of 7 astronomers, given the nicknames Seven Samurai at a 1986 workshop, and including Sandra Faber, Alan Dressler, Donald Lynden Bell, and others, published landmark papers documenting this large-scale motion and naming the unseen attractor. They called it the Great Attractor. It was a name that sounded like science fiction, but the data was real. The local group and everything around us was being pulled toward a gravitational concentration roughly 150 to 250 million light-years away of unknown nature, whose mass was estimated to be tens of thousands of times that of the Milky Way. For decades, the Great Attractor remained partially mysterious. Subsequent observations, especially in the X-ray and infrared parts of the spectrum, where dust does not block our view as effectively, revealed that the attractor was associated with a massive cluster of galaxies called the Norma cluster, and beyond it, a still larger concentration of galaxies called the Shapley supercluster, hundreds of millions of light-years away. The picture that emerged was that our local motion is part of an even larger flow, a current of galaxies pouring toward a region of unusually high galactic density, a place where the universe just happens, by the accidents of cosmic structure formation, to have piled up more matter than average. We are caught in that current. We are flowing with it, and the speed of the flow is impressive. The local group is moving, relative to the average local distribution of galaxies, at roughly 630 kilometers per second. 630 kilometers per second. 3 times the Sun's orbital speed around the galaxy, many tens of times the Earth's orbital speed around the Sun. The local group, our entire neighborhood of galaxies, is being pulled through space at an extraordinary rate, and we are coming along for the ride. This number, 630 kilometers per second, is one of the most precisely measured quantities in cosmology, and it is measured against perhaps the strangest reference frame imaginable, the cosmic microwave background, the oldest light in the universe. To explain how this measurement works, we need a brief detour into the structure of the cosmos itself. About 13.8 billion years ago, the universe began. It expanded from a state of extraordinary density and temperature, cooling as it expanded, and over hundreds of thousands of years, it transformed from an opaque plasma of hot ions into a transparent gas of neutral atoms. At the moment of that transformation, roughly 380,000 years after the beginning, the photons that had been bouncing endlessly off charged particles were suddenly free to travel. They streamed out across the expanding universe. Most of them are still streaming. They have been traveling for almost the entire age of the universe, redshifted by cosmic expansion into microwaves now, wavelengths that no human eye can see. They fill space. Every cubic centimeter of the universe contains hundreds of these photons. The residual heat of the original hot, dense beginning cooled now to a temperature of about 2.7 degrees above absolute zero. This is the cosmic microwave background, the CMB. It is the closest thing the universe has to a still photograph of itself, an image of a moment 13.8 billion years ago when the cosmos went transparent. It is incomprehensibly uniform. The temperature varies across the entire sky by only a few parts in 100,000. Almost the same temperature everywhere you look. Almost. There is one large, smooth variation, a single dominant pattern that overwhelms all the small fluctuations. The sky is slightly warmer on one side and slightly cooler on the opposite side. Very slightly. The hot side is about a few thousandths of a degree warmer than the cool side, and the warm and cold spots lie on directly opposite parts of the sky. This pattern is called the CMB dipole. It was first detected in the late 1960s and confirmed by the COBE satellite in the early 1990s, and refined dramatically by the WMAP and Planck satellites in the following decades. And here is what it means. The CMB dipole is not a feature of the early universe. It is a feature of our motion through the universe. We are moving through the bath of microwave photons that fill space. And just as a car driving through rain meets more drops on its windshield than on its rear window, our planet, our galaxy, our entire local group is meeting more photons head-on than from behind. The photons we are moving toward are slightly blue-shifted, slightly hotter. The photons we are moving away from are slightly red-shifted, slightly cooler. The dipole is the signature of our motion, written across the oldest light in existence. When astronomers correct for the Earth's motion around the Sun's motion around the galaxy, and the Milky Way's motion within the local group, they find that the entire local group is moving relative to the CMB at about 630 kilometers per second in the direction of the constellations Centaurus and Hydra toward the Great Attractor and beyond. The Sun itself, once you fold in its own motion within the local group, ends up moving through the CMB at roughly 370 kilometers per second toward a slightly offset point near the constellation crater on the boundary of Leo. This is, in some sense, the closest thing we have to an absolute frame of reference. The CMB fills the universe. It is the same age as the universe. It is the radiation left over from the moment when the cosmos became transparent. If you wanted to define what it means to be at rest in the universe, the most defensible definition would be at rest with respect to the CMB. And by that definition, our entire local group is moving at 630 kilometers per second. The textbook answer is that the Earth orbits the Sun. The textbook answer is correct in the Sun's reference frame. The richer answer is that you are spinning on the Earth. The Earth is orbiting the Sun. The Sun is drifting toward Hercules at 20 kilometers per second relative to the local stars. The Sun is orbiting the galactic center at over 200 kilometers per second. The Milky Way is approaching Andromeda at over 100 kilometers per second, and the entire local group is racing toward the Great Attractor at over 600 kilometers per second. 6 layers of motion, 6 superimposed velocities. None of them subtract cleanly from the others because they are pointed in different directions in space. The Earth's orbital plane is tilted relative to the Sun's path through the galaxy. The galaxy's plane is tilted relative to the direction of the local group's motion. The local group's motion through the CMB is at yet another angle. The total motion of your body right now through the CMB rest frame is the sum of all of these, and it works out to roughly 370 kilometers per second, about 1,300,000 kilometers per hour, depending on the time of year and the time of day, because the smaller motions add or subtract from the larger ones as the geometry shifts. 370 kilometers per second through the CMB. That is your true cosmic velocity in the most absolute frame we can define, right now. As you sit or stand or lie perfectly still in your perception, your body is moving through the bath of ancient light at a speed that would carry you from London to New York in 15 seconds. Stay with that. Stay inside it. The chair you are sitting in is moving. The bed you are lying on is moving. The walls of your room are moving. The whole planet is moving. The whole star system is moving. The whole galaxy is moving. The whole local cluster is moving, all in the same direction, all at the same speed. And that is why you do not feel any of it. Shared motion is invisible. But the photons of the CMB are not coming along for the ride. They are stationary in their own way, stationary relative to the average expansion of the universe. And our motion through them is real and measurable and constant and unimaginably fast. That is the picture in its fullest current form. 6 layers of motion, 6 superimposed velocities. The Earth's spin, the Earth's orbit, the Sun's local drift, the Sun's galactic orbit, the Milky Way's approach to Andromeda, and the local group's flow toward the Great Attractor. Each one was discovered separately. Each one required new instruments, new techniques, new generations of astronomers to confirm. The first was confirmed by Bessel in 1838. The last was confirmed by satellites launched in the 1980s and beyond. The full picture, the one we have just laid out, has only existed for about 30 years. Anyone born before 1990 lived their childhood without knowing the speed at which they were moving through the cosmic microwave background. The local group's velocity through the CMB was not refined to its current precision until the Planck satellite results in the early 2010s. We are still, in many ways, in the earliest stages of understanding our own motion, and the picture is not complete. The Great Attractor is itself part of a larger structure. In 2014, an international team of astronomers led by R. Brent Tully at the University of Hawaii published a paper redefining our place in the cosmos at an even larger scale. By analyzing the motions of thousands of galaxies in our part of the universe, they identified a vast, coherent structure that they named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters, roughly 500 million light-years across, containing about 100,000 galaxies, including the local group, the Altim Virgo supercluster, the Great Attractor region, and much more. Within Laniakea, all of these structures appear to flow toward a common gravitational basin near the Great Attractor and the Shapley supercluster beyond it. Though follow-up studies have suggested that Laniakea may not be tightly gravitationally bound and may disperse over time as the universe expands. So the local group is not just falling toward the Great Attractor, it is part of Laniakea. The Great Attractor is itself a feature within Laniakea. And Laniakea, in turn, is one of many superclusters, drifting in patterns we are still mapping, in a universe whose largest scale flows we are still measuring. There is a sense in which the picture, even at this scale, is not finished. We know the local group's velocity through the CMB very precisely. We know it is moving toward the Great Attractor and Laniakea's gravitational center. But we do not yet know with certainty whether there are larger flows beyond, whether Laniakea itself is being pulled by some still larger concentration of mass in a current we have not yet measured. Some studies suggest there might be. Others find no evidence of motion at scales larger than Laniakea. The question is genuinely open. We do not know how many more layers of motion there might be beyond the 6 we have established before we reach the cosmic ground floor. And it is possible, given the limits of cosmology, that we will never know. The observable universe has an edge. The light from beyond that edge has not yet had time to reach us. Whatever is happening out there, whatever larger flows might exist, may simply be inaccessible to measurement. We have built the most precise instruments we can. We have measured everything we can reach. And we have arrived at 6 layers of motion, and we cannot say with confidence whether that is the complete list. Take a moment with that. The science of cosmic motion is younger than your grandparents. The CMB dipole was first identified in the lifetime of people still alive today. The Great Attractor was named less than 4 decades ago. Laniakea was defined in 2014. We are not looking at a closed and finished picture. We are looking at a picture that is still being painted, still being argued over, still being refined by every new generation of telescopes and satellites and software pipelines. Every number we have stated has error bars. Every velocity has uncertainty. Every direction has been refined and re-refined. The Sun's orbital speed around the galaxy has been revised upward and downward multiple times in the last 20 years. The local group's velocity through the CMB has been refined as new CMB measurements have improved. Now we need to step back and ask a different question. We have accumulated motions. We have stacked frames. But what does it actually mean to say the Sun is moving? What does it mean for the solar system to have a velocity? Is there a true answer? Is there a real frame of reference, hidden somewhere beneath all these layers, against which the absolute motion of the Sun could be defined? Or is the whole concept of motion, at the deepest level, a kind of illusion, an artifact of comparing one thing to another, with no privileged truth lying beneath? Let us linger on the structure of motion itself for a moment, because this is where a great deal of confusion lives. Newton, in the 17th century, believed in absolute space and absolute time. He believed there was a true rest frame, a privileged background against which all motion could be measured. The Earth, in his picture, was really moving. The stars were really mostly fixed. The cosmos had a hidden geometry, and motion against that geometry was an objective fact. Einstein, in 1905 and again in 1915, demolished this picture. There is no absolute space. There is no absolute time. There is no privileged frame of reference against which motion has a true value. All motion is relative. All velocities depend on the observer. The Earth is moving relative to the Sun. The Sun is moving relative to the galaxy. The galaxy is moving relative to the local group. But none of these motions has any deeper meaning than the comparison itself. There is no view from nowhere. There is no place from which the universe can be observed without participating in some specific frame. This is one of the most counterintuitive truths in physics, and it has implications for everything we have just said. When we said the Sun is moving toward Hercules at 20 kilometers per second, we meant relative to the average motion of nearby stars. The Sun is approaching the constellation Hercules at 20 kilometers per second. We did not mean, and could not have meant, that the Sun is moving in any absolute sense. There is no absolute. The same is true for every velocity we have stated. 220 kilometers per second around the galaxy, relative to the galactic center. 630 kilometers per second through the CMB, relative to the cosmic microwave background. Each number depends on the frame. Each frame is just another object in motion. Yet, and here is the fascinating part, The CMB rest frame does have a kind of special status. Not because it is absolute in Newton's sense. It is not. But because it is the frame in which the universe on average looks the same in every direction. It is the frame in which the early universe was nearly at rest. It is the frame in which the cosmic expansion itself is most simply described. If you wanted to pick a frame that is, in some sense, the universe's own preferred frame, you would pick the CMB rest frame. And our motion relative to it is real and measurable and built into the largest scale structure of the cosmos. So we live in a universe without absolute motion, but with a kind of natural reference frame, against which we are racing at 370 kilometers per second. 6 frames of motion, 6 layers of velocity. The sun, dragging the planets, dragging us through a cosmos of nested currents, none of them final, none of them complete, none of them ever quite still. Now we need to ask harder questions. What does any of this mean? What does it mean to be a creature whose home is a moving target? What does it mean to learn, after thousands of years of believing in solid ground, that there is no solid ground anywhere? That the floor beneath your feet is not floor, the room around you is not room, the planet is not anchored, the sun is not anchored, the galaxy is not anchored, and even the universe itself, on its largest scales, is in flow? What does it mean that the Earth has never been in the same place twice? That every birthday, every anniversary, every this time last year is a memory of a location that no longer exists? That the night sky you see tonight is not the same night sky you saw a year ago, because the stars themselves are also in motion, drifting against one another, drifting against the galaxy, drifting against the larger structures, and the sun is moving among them, and we are moving with the sun. What does it mean that the very concept of motion has no ultimate ground? That every velocity we have measured is just a comparison, a relationship between objects with no deeper truth beneath it? What does it mean that we cannot know, and may never know, whether there are still larger frames beyond the ones we have mapped, whether Laniakea itself is being pulled by something larger, whether the cosmic microwave background is, in some unimaginable sense, also moving relative to something we cannot see? What does it mean to call any place home when the place itself is in motion and the motion never stops? What does it mean to stand still? These are not rhetorical questions in the dismissive sense. They are real questions. They have no clean answers, but they sit at the center of what cosmic motion does to us when we let it in. We came to this topic to learn about the geometry of orbits, about the speeds of stars, about the structure of the galaxy. We came for facts. And the facts have led us, by their own internal logic, to a place where the deepest assumption of our daily lives, that we are standing still on solid ground, has dissolved entirely. There is no still. There is no ground. There is no fixed point. There is only motion, layered on motion, layered on motion, all the way down, until we reach the limit of what we can measure. And even then, we cannot prove that the layers stop. The cosmos may be turtles all the way down, or rather, currents all the way down, frames of reference all the way down, with no foundation, no bedrock, no place where anything is finally at rest. There is a paradigm shift hiding in this picture, and it is worth naming it directly. Most of us, when we first learn the sun-centered model of the solar system, treat it as the final demotion. The Earth is not the center of the universe. It is a planet orbiting a star somewhere in a galaxy, in a universe that does not revolve around us. We accept that demotion, and most of us think the demotion has finished, but it has not. The sun is also not the center. The galaxy is also not the center. The local group is also not the center. There is no center. The hierarchy of demotions does not stop with the Earth. It continues all the way out until the very concept of center becomes meaningless. The cosmos is not a sphere with a middle. It is a flowing, expanding, tangled fabric in which no point has any privileged claim. And the motions we have measured are not motions toward any particular destination. They are motions within an open-ended geometry with no shore in sight. Stand on a hilltop on a clear summer night, the kind of night where the air is cool and the wind has died and the stars feel close. Lie on your back in the grass and let your eyes adjust. The Milky Way, if you are far enough from city light, will rise overhead like a river of pale smoke, arcing from one horizon to the other. There are stars in that river, billions of them, packed so densely that they blur into a single soft glow. There are dust lanes too, dark fissures running through the river where the light is blocked by clouds of cold matter, sketching the spiral arms in shadow. The whole structure tilts above you, vast and silent, and for a long moment, lying there, you cannot tell whether you are looking up or looking down. The Earth feels small beneath your back. The stars feel close to your face. The river of light could be a ceiling or a floor. Stay there. Stay on the hilltop, with the grass beneath you and the river above. Now feel, slowly, what we have just learned. The Earth is not still. The hilltop is moving. You are moving with it. You are spinning, slowly beneath the stars, at hundreds of kilometers per hour. You are orbiting the sun, somewhere in the curve of Earth's annual path, at 30 kilometers per second. The sun is dragging you toward Hercules, which is up there somewhere among the stars you can see, at 20 kilometers per second. The whole local neighborhood is curving around the galactic core at over 200 kilometers per second, in a direction roughly toward the constellation Cygnus, which is also up there, riding high in summer skies. The whole Milky Way is falling toward Andromeda, which you cannot quite see from this hemisphere this season, but which is up there too, in some direction, gently accelerating toward us across 2.5 million light years. And the whole local group is racing towards Centaurus, low in the southern sky, at 630 kilometers per second, hauled by the Great Attractor and Laniakea and whatever lies beyond. You are not still. You have never been still. You will never be still. The hilltop you are lying on is, at this moment, in a place no human has ever been before, in absolute spatial coordinates. The grass beneath you, in those same coordinates, has been swept forward by hundreds of kilometers in just the time it has taken you to listen to this passage. The stars above you are moving too, drifting against each other, drifting against the galaxy, drifting against the larger flows. The whole night sky is a snapshot of motions in progress, frozen by the slowness of human perception into the illusion of a fixed pattern. But it is also, somehow, unbearably peaceful. That is the strange gift of this perspective. The motions are so vast, so far above the scale of any single human life, that they do not feel violent. They feel slow. They feel inevitable. They feel like tides. The Earth turns once each day, and the sun rises, and the stars wheel overhead, and somewhere, very far away, the galaxy is curving through space, and we are part of the curve, and we always have been. The hilltop is moving, but the hilltop has been moving for as long as it has existed, and so has every other hilltop on every other planet, around every other star. There is nothing exceptional about your motion. It is the ordinary condition of being part of the universe. Everything moves. Everyone moves. Every atom in your body has been carried by these layered currents across distances no eye could ever see. There is something in this realization that reminds me of the way a river feels when you wade into it. At first, the current pulls at your legs and feels like a force. You brace against it. You feel the water moving past you. But if you stand long enough, with your feet planted, you stop noticing the current. The water is just there. The motion becomes the background. You are no longer being pulled by the river. You are part of the river, and the river is part of the place. The motion becomes stillness. The flow becomes the floor. That is what it means to live in a moving cosmos. The motions do not feel like motion. They feel like the structure of reality itself. They are the river we are all standing in, and we have never been outside it, and we have never been at rest. The stillness we feel is not the absence of motion. It is the perfect synchronization of motion. Everything around us is moving with us, and the shared motion becomes invisible, and we call that condition rest. But there is no rest. It is the most active state imaginable. Right now, in the time it has taken you to read this section, your body has moved through the cosmic microwave background by more than 100,000 kilometers. Picture that distance, the diameter of the Earth. You have, in just the last few minutes, traveled the equivalent of several Earth diameters through the universe's most fundamental reference frame. And you have not noticed. You have not felt anything. The chair has not shifted. The walls have not lurched. The motion is invisible because everything is participating in it, including the photons of light that bounce off the walls and reach your eyes, including the molecules of air that carry the sound of your own breath, including every nerve and atom of your body. The motion is invisible because, locally, there is nothing it could be measured against. Stay with the hilltop a moment longer. Feel the grass beneath your back. Feel the cool air on your face. Feel the slow, patient turning of the planet as the stars wheel overhead. The wheeling is real. The motion is real. The hilltop is being carried through the cosmos at a speed that defies human imagination. And yet, it feels like nothing. The peace of a clear summer night lying on a hilltop is not a fiction. It is the strange, lovely consequence of being completely synchronized with the river you live inside. This is the gift of cosmic perspective, not the loss of grounding. The discovery that grounding was always relative. The discovery that the floor beneath your feet was never anchored, that the hilltop was never still, that the earth was never solid in the sense you imagined, and that this is fine. This is how it has always been. This is how every creature that has ever lived has lived. The dinosaurs walked on a moving earth. The first single-celled organisms drifted in oceans on a moving earth. The earliest hydrogen atoms in the universe were already moving relative to one another, even before any galaxies formed. Motion is not the disturbance of stillness. Motion is the original condition. Stillness, if it ever existed, is the rare exception, and we have never directly observed it. Notice, too, how the largest motions are also the slowest. The Earth's spin completes once per day. The Earth's orbit completes once per year. The Sun's local drift would, if it kept on its current course, take perhaps 150,000 years to carry us from one side of the local bubble to the other. The Sun's galactic orbit takes 250 million years. The Milky Way's collision with Andromeda will take 5 billion years to complete. The local group's flow toward the Great Attractor is a journey that will not arrive within the lifetime of our species, our planet, or our star. The bigger the motion, the slower the clock. And so, paradoxically, the largest velocities feel the most static. We can see no change year after year in the configuration of the constellations. The night sky of your childhood is, for all practical purposes, the same night sky you will see in your old age. The motion is real, but it operates on timescales so vast that human lives do not register against them. Take this in slowly. The cosmic motions are happening at speeds that are, in absolute terms, breathtaking. Hundreds of kilometers per second, thousands of kilometers per second when you sum across frames. But the distances they are traversing are so vast that the visible change on any human timescale is essentially zero. The same constellations were overhead when Cleopatra ruled Egypt. The same Polaris pointed roughly north when the pyramids were built. The same Milky Way arched overhead when our species first painted on cave walls. The motions are real, but the universe is so large that even at these speeds, we are barely scratching the surface of any motion's full extent. This is also why the experience of a clear, still night feels so eternal. The peace is not a denial of the motion. It is a result of being so deeply embedded in it. We are part of a process that takes billions of years to unfold, and in any given moment of human time, almost nothing visible has changed. The hilltop is the same hilltop our ancestors stood on. The stars are the same stars they saw. The Milky Way arches in the same direction. The seasons turn in the same patterns. The sun rises in the east and sets in the west, and the world feels old and patient and reassuring. None of this is wrong. The patterns are real. The patience is real. We have just learned that beneath the patterns there is a vast and ceaseless current. But the current is so slow by our standards that it does not disturb the stillness of the moment. And let your shoulders drop. Pause, and let your jaw soften. Pause, and feel, for one breath, the long, slow drift of the world. There is one more place to visit before we approach the larger reckoning of what all of this means. We have spoken of the sun's motion through the local neighborhood, and through the galaxy, and through the local group, and through the CMB. We have not yet spoken much of what is happening to us right now, locally, as the sun moves. We are passing, as I mentioned earlier, through a region of slightly denser gas called the local interstellar cloud. We entered it sometime in the last 100,000 years. We will leave it sometime in the next 50,000. While we are inside it, the heliosphere, the bubble of solar wind that protects the inner solar system from the harshest forms of cosmic radiation, is being shaped by the cloud's pressure. Think of the heliosphere as a kind of soft shell. The sun is constantly emitting a stream of charged particles, the solar wind, in all directions. That wind, traveling outward, eventually meets the gas of the surrounding interstellar medium and slows down. The boundary where it slows is called the heliopause, and it lies somewhere around 120 astronomical units from the sun, far beyond the orbit of Pluto, far beyond the Kuiper belt, in the deep edges of the solar system's outer reaches. The two Voyager spacecraft, launched in 1977, have crossed the heliopause and are now in true interstellar space, sending back faint signals that take more than 20 hours to reach Earth. They are, in a real sense, the only human-made objects ever to have left the sun's influence and entered the surrounding galactic environment. The shape of the heliosphere is not a sphere. The sun's motion through the local cloud distorts it. The leading edge in the direction of our motion is compressed. The trailing edge behind us is stretched. We push the gas in front of us. The gas behind us flows back into the wake. The shape is something more like a comet, or a teardrop, or a cocoon, long behind us, blunt in front. We did not know any of this with confidence until the early 21st century, when missions like IBEX, Interstellar Boundary Explorer, launched in 2008, began mapping the boundary directly. The heliosphere's true shape is still being argued over. Some studies, including those by David McComas and his colleagues, suggest a more croissant-like or crescent shape, much shorter behind us than the older long-tail model implied. Others continue to defend the long-tail picture. The science is ongoing. We do not yet know, with full confidence, the shape of our own solar system's outer boundary. But the point is this: the boundary is shaped by motion. The shell around our home is dented and stretched by our passage through the local cloud. If we were not moving, the heliosphere would be roughly spherical. Because we are moving, it is not. Our motion is written into the very shape of our home, and that motion has been built into its geometry for as long as the sun has existed. We have always been moving. The heliosphere has always been a teardrop. We have never lived inside a sphere. We have always lived inside a wake. Take a moment to absorb that. Even at the smallest scale of the solar system itself, even before you zoom out to the galaxy, the motion of the sun shapes the protective shell around the planets. The bubble that shields us from cosmic rays, that gives us breathable air and survivable surface conditions, is not a static dome. It is a dynamic wake. It is being continually pushed out in front of us by our forward motion through the gas of the interstellar medium and stretched out behind us like the contrail of an airplane. We live inside that contrail. The protection it offers is the protection of motion itself. This is the second paradigm shift the topic asks of you. Not just that we are moving, but that the very conditions for life on Earth are partially dependent on that motion. The heliosphere protects the inner solar system from cosmic rays. The shape of the heliosphere depends on the sun's velocity through the local interstellar gas. If the sun were to decelerate, which it will not, but as a thought experiment, the heliosphere would change shape. If the sun's path took us into a denser cloud of gas, the heliosphere might be compressed. Some researchers, including Priscilla, Frisch, and others, have explored whether the sun has, in past epochs, encountered denser clouds of interstellar gas, and whether such encounters might have altered the radiation environment near Earth in ways that could have left fingerprints in the geological record. The evidence for such effects is suggestive, but not conclusive. We do not yet know, but the question is taken seriously because the principle is sound. Our motion through the galaxy shapes our local environment, and our local environment shapes life. We are not just moving through the universe. We are being shaped by our motion. The bubble we live in is the consequence of our passage. The protection we receive is the result of our flow. We are not visitors in a static cosmos. We are participants in a moving one, and the motion is written into us, into our home, into the conditions of our existence. Now, having spent this time on the hilltop, having let the motion become a kind of stillness, having seen how motion shapes the very shell of our solar system, we have to take the final, hardest step. We have to ask what all of this means for the human creatures who are doing the looking. What does it mean to be, as you are right now, a small, warm-blooded animal on the surface of a moving rock, orbiting a moving star, embedded in a moving galaxy, embedded in a moving cluster, all of it racing through a moving cosmos toward destinations no one alive will ever see? What does it mean to know this? What does it mean to live with this knowledge day to day while still going to work, still feeding the children, still tending the garden, still grieving the dead, still loving the people you love? There is a beautiful historical parallel for the kind of recognition we are arriving at, and it is worth telling, because it shows that humans have been here before. Not in the same form, but in a form of equal weight. In 1609, Galileo Galilei pointed a telescope at the night sky for the first time and saw, among other things, 4 small points of light orbiting Jupiter. He watched them for weeks. He saw their patterns repeat. He realized he was watching a small system of moons circling a planet in the same way that the Earth was supposed to circle the Sun in the new heliocentric model. The Jovian moons were a miniature model in miniature of the entire heliocentric universe. They proved by direct observation that not everything in the cosmos orbits the Earth. They demolished in a single set of observations the geocentric model that had reigned for over 1,000 years. Galileo was not the first to suggest the Earth moved. Aristarchus had proposed it nearly 2,000 years earlier. Copernicus had revived it in the previous century, but Galileo was the first to provide direct telescopic evidence, and he understood the implications. He wrote, with care and with clarity, about what he had seen. He defended the heliocentric model. He was condemned by the church. He spent his last years under house arrest. He was, by some accounts, broken by the experience. But he had, in his own lifetime, done something irreversible. He had moved the Earth. That phrase, "he moved the Earth," is meant in 2 ways. He proved the Earth was moving, and he changed the way humans thought about themselves by showing that the planet beneath their feet was not the still center of the cosmos. Both meanings are true, and the second one is, in many ways, the larger achievement. The Earth had always been moving. What changed in 1609 was the human understanding of that motion. We were not given a new motion. We were given new self-knowledge. We learned what we had always been doing. We are, right now, in a similar moment. Not as dramatic, perhaps, because it has unfolded over decades rather than years, and because no church has condemned anyone for the discovery, but as profound. We have learned, in the last century or so, that the Sun is moving through the galaxy, that the galaxy is moving within the local group, that the local group is moving within Laniakea, that all of it is moving relative to the cosmic microwave background. We have learned that there is no privileged frame, no ultimate rest, no still point at the heart of the cosmos. We have learned that the demotion that began with Copernicus does not stop with the Earth. It continues all the way out to every scale we have measured. And yet, walking down the street, going to the grocery store, sitting on a porch in the evening with someone you love, none of it feels different. The discoveries do not change the texture of your day. The hilltop is still the hilltop. The grass is still the grass. The stars are still the stars. And they still feel close. And they still feel like home. The motion does not interrupt the peace. The peace, in fact, is the motion, perceived from inside. This is the deepest gift. This is the lesson the cosmic perspective offers when we let it land. We do not have to choose between knowing the truth and feeling at home. We can know that we are racing through the cosmos at 1,000,000 kilometers per hour, and we can still feel the warmth of the sun on our skin, and we can still call the place we live home, and we can still mean it. The motion does not erase the home. The motion is the home. We have always lived inside a moving thing, and we have always called it home, and we have always been right to do so. So let us gather what we have seen. We began with a star. We picked one out of the night sky and held it in our gaze and noticed that we believed we were standing still. We are not. We never were. The body that held the gaze was spinning on the surface of a planet at over 1,000 kilometers per hour. The planet was orbiting a star at 30 kilometers per second. The star was drifting toward Hercules at 20 kilometers per second, relative to the local stellar neighborhood. The star and its neighbors were curving around the heart of the Milky Way at over 200 kilometers per second. The Milky Way was approaching Andromeda at over 100 kilometers per second. The local group of galaxies was racing toward the Great Attractor and Laniakea at 630 kilometers per second relative to the cosmic microwave background. 6 layers of motion, 6 superimposed velocities, none of them subtracting cleanly from the others because they pointed in different directions in space, and the total motion of the body that held the gaze through the most absolute frame the universe makes available to us was roughly 370 kilometers per second, faster than any rocket ever built, faster than any speed a human will ever directly perceive, constant, ceaseless, invisible. We watched that motion shape our home. The heliosphere is not a sphere. It is a teardrop, a wake, a contrail, dented in front by the sun's passage through the local interstellar cloud, stretched out behind us in the direction we have already left. We do not live inside a static bubble. We live inside the trail of our own motion, and the trail has been there for as long as the sun has existed. The protection it offers against the cosmic rays of deep space is the protection of speed. We are kept safe, in part by the very motion that we cannot feel. We watched the Earth's orbit dissolve from a flat ellipse into a long helix, a corkscrew threading through the galaxy, never closing, never returning to the same place. We saw that every birthday, every anniversary, every time we said, "This time last year," was a memory of a place that no longer exists in the larger frames of reference. We saw that the orbit is a useful local fiction, a pattern that makes sense from the sun's vantage, but dissolves into a spiral the moment we step outside. We saw that the textbook diagram is not wrong exactly, but profoundly local, true within its frame, untrue beyond it. We watched the Milky Way reveal itself to be one galaxy among an uncountable number, only confirmed as such in the 1920s by Edwin Hubble's observations of Andromeda. And we watched our place within it be located in a quiet suburb, 26,000 light-years from the galactic core, in the Orion Spur, between the Sagittarius Arm and the Perseus Arm, in a part of the disk gentle enough that life had time and space to develop without being cooked or starved. We watched the sun complete fewer than 20 galactic orbits since the planet formed, and we noted that the number sounds small only because the galaxy is so large. The sun is barely beginning to learn the shape of its own path. We watched William Herschel in 1783 deduce from the patterns of stellar drift that the sun itself was moving. We watched Friedrich Bessel in 1838 prove the Earth's motion by measuring the parallax of a single star. We watched the 7 astronomers in 1986 name the Great Attractor. We watched Mark Reid and his colleagues in 2014 refine the sun's galactic velocity using radio observations of cosmic masses. We watched R. Brent Tully and his team in the same year define Laniakea, our home supercluster of superclusters more than 500 million light-years across. We watched the science of cosmic motion be built, brick by named human beings working with telescopes and satellites and software over the course of 2 centuries. Most of it in the last 50 years, much of it in the last 2 decades, some of it still unfinished. We saw that the picture is not closed. We do not know whether the local group's motion is final or whether Laniakea itself is being pulled by something larger. We do not know the precise shape of our heliosphere. We do not know whether the sun's vertical bobbing through the galactic disk has shaped the history of life on Earth. Some researchers think it has. Others think it has not. The questions remain open. The science is still being done. And we saw finally what cosmic motion does to us when we let it land. It does not erase the home. It reveals what the home has always been. The hilltop has never been still. The grass has never been still. The stars have never been still. We have always lived inside a moving thing, and we have always called it home, and we have always been right to do so. The peace of a clear summer night lying on a hilltop is not a denial of the motion. It is the consequence of being completely synchronized with it. Shared motion is invisible. We are part of the river. The river is part of the place. The flow is the floor. There is something quietly noble in what humans have done with this knowledge. We could have refused it. We could have insisted on the textbook ellipses and the still sun and the fixed earth. Many of our ancestors did. Galileo's contemporaries did. The first astronomers to propose stellar motion were ignored and then dismissed, and then slowly, reluctantly believed. But over the centuries, we accepted the demotions one after another. We accepted that the Earth moves. We accepted that the sun moves. We accepted that the galaxy moves. We accepted that there is no privileged frame, no absolute rest, no center to the cosmos. And in accepting, we have not become smaller. We have become larger. We have grown to encompass a perspective that no creature on Earth had ever held before. We have made ourselves at home in a moving universe, and the home is more interesting than the still version we used to imagine. Look up at the night sky now and pick a single star. Hold it in your gaze. You know now that you are not standing still beneath it. You know now that your body is moving through the galaxy at speeds no rocket has ever matched, and that the motion is real and constant and invisible and beautiful. You know now that the diagram in the textbook was a useful local fiction, and that the real shape of your home is a long, slow corkscrew threading through the dark, and that the corkscrew is itself part of a larger curve, and that larger curve is itself part of a still larger flow, and that the flows go all the way out as far as we can measure, and possibly further than we will ever measure. You know now that the Earth has never been in the same place twice, and never will be. You know now that every place you have ever loved has been moving the entire time you loved it. You know now that the people you have lost did not leave from a fixed location, because there are no fixed locations, and the place where you said goodbye to them has long since been swept forward by the sun's passage through the galaxy. You know now that the photons from the star you are looking at left it long before you were born, and have been traveling toward you across distances no eye can directly grasp, and have arrived just now, just for you, just at this moment, having missed every other moment of your life by some specific number of years. You know now that the cosmic microwave background fills every cubic centimeter of space, and that you are passing through it at 370 kilometers per second, and that this number is the closest thing the universe will ever give you to a true cosmic velocity, and that even this is, in the deepest sense of physics, just another comparison, another frame, another relationship between things in motion. You know now that there is no still. There never was, there never will be, and the absence of still is not a loss. It is the structure of being. If this changed how you think about the solar system, then the time was well spent. Thank you sincerely for staying through all of it. Thank you for letting the motions land. Thank you for the patience to follow a thread from a star in the night sky to the cosmic microwave background, and back again. Thank you for being one more pair of eyes, one more body, one more mind, riding the long, slow helix of the Earth around the sun, riding the longer, slow helix of the sun around the galaxy, riding the long, slow flow of the galaxy through the cosmos. You have been moving the whole time. You will keep moving long after this video ends. The motion does not stop. Look at the star one more time. The single star you picked at the beginning. It is still there. It has moved slightly since you began listening, drifted some small fraction of a degree against the background of more distant stars. You have moved more. The hilltop you imagined yourself lying on has been carried forward by the sun's passage by tens of thousands of kilometers in just the time we have been speaking. The chair you are actually sitting in has been carried forward by hundreds of thousands. The constellation Hercules is still up there, somewhere, in some direction, and we are still racing toward it, and we will still be racing toward it long after this night has ended. The star you picked is not anchored. The sun is not anchored. The galaxy is not anchored. Nothing is anchored. And yet, here you are, held by the gravity of the planet, held by the warmth of the sun, held by the long arms of the Milky Way, held by the gentler grip of the local group, held by the slow tide of Laniakea, held in motion by every scale of the cosmos at once. That is what home means in a moving universe. That is what it has always meant. The diagram in the textbook was a comforting fiction, but the truth is more comforting still. We are not adrift. We are riding, and we have always been riding. And the river has always carried us, layer upon layer, frame upon frame, all the way out into the immeasurable heaven that is, somehow, our address. Hold the star a moment longer. Then let your gaze soften. Let the night settle around you. The motion does not need your attention. It will continue without it. Tomorrow the sun will rise. That is, the earth will turn so that the part of it you are standing on faces the sun once again. And the day will begin, and the small motions of human life will fill it. And beneath all of them, the great motions will continue, slow and patient and ceaseless, carrying you into a future no telescope has yet seen. That is the picture. That is how the solar system actually moves through space, not in a textbook diagram, not in a flat ellipse around a still sun, but in a long helix through a moving galaxy, inside a moving cluster, inside a moving supercluster, riding a flow whose final shape we have not yet measured and may never measure, and which is, regardless, our home. Sleep well if you are sleeping. Rest easy if you are resting. The motion will hold you. It always has.